Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today the Quantum Architecture and Computation Group is welcoming Nathan Wiebe here to talk with us. He is a postdoc at the Institute for Quantum Computation, IQC, at University of Waterloo. And today he's going to be talking about designing quantum circuits for efficiently simulating many-body dynamics. So Nathan, I'll turn it over to you.
Great, thank you very much, Krista. So thanks a lot for coming. Well, you've heard what I'm going to be talking about. This is work that I've done collaboratively with Sadek Reisi as well as Barry Sanders. And the outline of the talk is laid out as follows. So first, I'm going to provide an introduction to quantum simulation algorithms. And then I'm going to discuss, by providing some simple examples, how to simulate a few very primitive many-body Hamiltonians. Then I'll use the intuition that we've developed from this discussion in order to show how to construct a circuit that automates a classical algorithm that automates all of this reasoning. And then finally, I'll discuss how these results can be optimized by grouping terms in appropriate ways for parallel execution. So, in general, quantum dynamics is known to be very hard to solve, or at least is believed to be very hard with the best known algorithms that we've got. I did a search, and the most sophisticated quantum simulation that I was able to find was performed by this supercomputer, and it was able to simulate quantum dynamics on a 42-qubit system at the cost of roughly $100 million. Now, this is something to me that was pretty impressive, because I've done these things by hand, and general dynamics, I have a really hard time pushing upwards of 20 qubits. 42 qubits is a substantial feat, especially because of the fact that it gets much harder as you try to make the simulator work for bigger and bigger systems. So, in general, the number of the computational resources needed in order to perform the simulation will scale exponentially with the dimension of the system. So, for example, if you've got 42 qubits, well, it took only one of those supercomputer clusters. But using optimistic scaling, we'd need 2 for 43, and so on and so forth. This gets absurd, because if we want to even simulate a modest scale quantum system, say 115 qubits, going through the math and computing the weight of all of the processors in the supercomputer required to simulate the 115 qubit system in the same amount of time, we'd require at least an amount of processor mass that's equivalent to the mass of the Earth. So something's wrong here, especially if we believe that nature contains 115 qubit systems in it, i.e. systems of, say, 115 interacting electrons. So how is nature getting away and answering these questions without requiring a supercomputer the size of the planet? And the answer, I believe, as well as many in my field believe, is through quantum information. So the basic idea is we'd like to get around this problem by exploiting quantum mechanics in order to simulate quantum mechanics. And the intuition works as follows. Let's imagine that we've got some physical system that we would like to simulate. And specifically, we have a quantum state that's in that physical system, and it follows some natural evolution described by a system Hamiltonian to a final state over here. We'd like to simulate that by taking this initial quantum state and constructing a state that's logically equivalent to it in a quantum computer. Then, instead of this nice, smooth evolution that we get by the Hamiltonian, we approximate the evolution by a sequence of quantum gates that are permitted for the particular quantum computer. The result of applying those quantum gates will be a quantum state that, if everything is done correctly, should be logically equivalent within some error tolerance to the actual state that we would have observed in the physical system. So that's the whole idea behind this method of using quantum computers to simulate quantum dynamics. There's some really big strengths and there's some really big limitations. So I'll start with the bad news first. The bad news is that, unfortunately, you actually get zero information out of this system by doing one simulation. I mean zero information, because of the fact you've got a quantum state and you haven't measured it. You haven't extracted any information from it. If you want to learn something from it, then you can perform a measurement. But the problem is, for certain things, you may require a large number of measurements. Like if you wanted to learn the quantum state in general, you'd have to do some process like quantum state tomography, and that's exponentially expensive. So you're not going to get an efficient estimate of the quantum state as a result of one of these simulation algorithms. Also, in order to guarantee that we can emulate the evolution with a small number of gate operations, we need to make several promises about the form of the system Hamiltonian we're simulating. This won't be efficient for all possible systems. But if these caveats are made, then we can find expectation values and certain eigenvalues by repeating the simulation a polynomial number of times and processing the data. So the other big strength about this is, unlike algorithms such as Shor's algorithm, we don't necessarily need very many qubits in order to outperform what the best classical computers can do, as the discussion previously about the mass of the Earth was hopefully alluding towards. So I'd like to now provide some background about how the field has progressed. Originally, this idea of simulation was proposed by Feynman when he was noting that he wasn't able to write very efficient simulation code for quantum systems, but quantum systems seemed to be doing it naturally. And this led him to propose the idea of a quantum computer. But since it took quite some time since then for somebody to actually formally talk about how to do these simulations. And the first case was done by Seth Lloyd in '99, where he showed how to simulate quantum dynamics in the restricted case that the Hamiltonian is a tensor product of sum of tensor products of low-dimensional systems. So that work was subsequently improved by Aronov and Andrew Childs and others. In 2007, this was improved further by Dominic Berry, Graham Mayokas, Richard Cleve, and Barry Sanders, who came up with substantial optimizations to the algorithm that caused it to run in near linear time as opposed to like quadratic time or t to the 3/2. Recently, myself and a few other co-authors have generalized these ideas to rigorously show how to simulate time-dependent Hamiltonians as well. So that's sort of the many of the most recent results involving quantum simulation algorithms. How are the complexity of these algorithms typically assessed? And the way they're assessed is in a very high-level perspective. Often what we're interested in is a number of times a Hamiltonian black box is queried. So this black box works as follows. You provide a quantum state that encodes a row and a column, and it outputs in another quantum state an encoding of the matrix element of the Hamiltonian, HXY. Also, there's an additional black box that's often considered that will tell you the locations of non-zero matrix elements. But those are the two things that are considered to be the resources that are required for these algorithms. And the cost is given by the number of accesses you have to make to this black box. And the best of those algorithms that I described previously has the following scaling for the number of calls that are needed. So it scales slightly worse than a fourth power of the sparseness of the overall Hamiltonian, nearly linearly with the norm of the Hamiltonian and the evolution time, and subpolynomially with the error tolerance.
Do you have a definition of d-sparse somewhere?
Of each what?
Of d, do you have a definition of d-sparse?
Sure. A matrix is a d-sparse if each row and column contains at most d non-zero matrix elements. Okay? So that is basically the results. Now, there's a bit of an issue that we would like. Unfortunately, to the best of my knowledge, very few ion traps have a black box. So the question is, how do we go about taking this from this theoretical description that uses this black box to something more fundamental that we could consider actually implementing? And in general, unfortunately, it's very difficult for an arbitrary black box to consider doing a circuit decomposition of that. However, for some particular cases, specifically local Hamiltonians, results are known. Recently, Weimer, Mueller, Buchler, and Lesanovsky found a trick that actually can be used in order to simulate many-body systems without requiring a black box or doing any of this sort of nonsense. So the main drawback behind their technique is, unfortunately, they went through the analysis and they were correct about their trick, but you have to have a lot of knowledge and a lot of intuition to see how to apply that trick to be able to simulate a general Hamiltonian. It's not something you can straightforwardly tell a computer to do, and it will output the correct result. Also, they don't use optimizations proposed by previous simulation schemes, such as the use of high-order integrators or other such tricks. And what we do is we rectify these two problems. We make it automatic so that a computer can directly output a quantum simulation circuit. And also, we include the optimizations that are used in the best simulation algorithms to date. So that's basically what we do. Now, just to give an outline for the rest of the talk, what I'm first going to do is I'm going to discuss, simulation of many-body Hamiltonians. And I'm going to define what I mean by a local Hamiltonian. Then I'm going to show how to simulate some extremely simple Hamiltonians and lead in eventually to the classical circuit building algorithm. So what do I mean by a many-body system? Well, this is probably the most trivial slide of all of them. What I mean is a system that has many interacting bodies. All right, so that's somewhat tautological, but there's many examples in physics that have these properties. For example, Ising models that have interacting magnetic dipoles on some sort of a lattice, or qubits in an optical lattice are all described by these many-body systems. Out of them, we're interested in a particular case. We're interested in k-local Hamiltonians. And these are Hamiltonians that are the sum of terms that are tensor products of at most k non-identity Pauli operators. So, for example, the following operator here, H, is two-local, meaning that it's a sum of terms that are at most tensor products of two distinct Pauli operators. So that's what I mean. And many important Hamiltonians end up falling into this category, like the Heisenberg model, Ising model, toric code Hamiltonian.
Plus Z1 plus Z2?
It should be tensor product identity on both of those cases. But yes. In this particular case, it should be tensor product identity on that side and tensor product identity on this side. So there's many cases of physically relevant Hamiltonians that fall into this class, and people would like to simulate them, but there aren't any efficient methods yet. So out of k-local Hamiltonians, there's actually two distinct classes that I'm going to talk about briefly in this presentation. And cases are physically local and just strictly k-local. And you notice there's actually a pretty big difference. The difference is if you make a graph of each qubit in the system and draw an edge between each qubit that directly interacts with each other, many physical models only have nearest neighbor interactions. So what that means is if you take a look at the graph, each vertex has constant degree for these physically local Hamiltonians. However, generic k-local Hamiltonians allow you to have a complete graph of interactions. So as you might imagine, this case is substantially simpler than a generic k-local case. And because of the fact that many physical systems fall into this category, it's worth us discussing the difference between the performance of our algorithms in this case and in that case. So how do we go about simulating these things? So I'm going to present the easiest possible Hamiltonian you can consider simulating of this form. It's a tensor product of k Pauli Z operators with a weighting term in front of it. So the way you simulate, the reason why this is the simplest is because of the fact that it's already diagonal in the computational basis. So what that means specifically is that if you act with this on a particular quantum bit string, it will just give you that quantum bit string back. So to see why this is so easy, let's consider the action of the time evolution operator, which is defined to be e to the negative I ht, on an arbitrary initial state. By decomposing this as a sum of different computational basis states, we end up getting that by definition. So since the Pauli Z operator just acts as a phase flip depending on whether the corresponding bit is 0 or 1, we can actually take a look at what this operator does. It will simply provide a phase flip depending on what the values of in this case, the first qubit is, the second qubit, and all the way up to the kth qubit. Here, I don't mean direct sum, I mean exclusive OR between all of these things. So what that means is that we can simulate the evolution by just simply doing a Z rotation on a qubit that encodes the parity. So if we can store the parity of all of these k bits here and perform a Z rotation on it, then we'll enact exactly this phase rotation that we end up seeing here. And that's the idea behind the simulation circuit. So the corresponding circuit that ends up doing this is as follows. It takes an initial qubit string, performs a controlled NOT gate on this last qubit to compute the parity, then does a Z rotation on that parity qubit, and undoes the computation of the parity. And again, we need to undo the computation of the parity to make sure that we don't require a very large number of ancilla bits to do this computation. So now that that's done, let's talk about a slightly more complicated example. Let's say that instead of Z tensor K, I switch the first two operators to poly X operators instead of Z. This makes it harder because poly X operators aren't diagonal. So we can't just do a rotation in the eigenbasis. Instead, what we need to do is we need to transform to the eigenbasis of this new Hamiltonian. And we do that by performing the Hadamard transform on the kth bit and the first bit. Then we can treat that as a Z rotation in its eigenbasis. And then we return to the computational basis via this transformation. Okay? So if we do that, then the resulting circuit looks identical, except now there's Hadamard transforms.
Shouldn't the Hadamard be reversed in one of the...
They're its own inverse.
Yeah.
Oh, they commute.
They commute. They're on
Okay.
different qubits. Yeah. So, but yes, you're right. If they didn't commute, then yeah. So that's the resulting circuit. And you can imagine Y is pretty much exactly the same. The only difference is if we replace those X's with poly Y operators, now we have to do a slightly more complicated diagonalizing operation. And the one that works is pi by 8 gate to the 6th Hadamard, and then its inverse on the other side. And you might be wondering why the 6 and a 2. Well, if you do pi by 8 times, then you end up getting the identity. So that's why it's 6 and 2. In order to make sure that we can represent these transformations as just Hadamard, pi by 8, and C naught, which are a universal set of gates. So that is the more complicated example. So with this, you can see how we can go about simulating any Hamiltonian of that particular form. That's a tensor product of X, Y, and Z gates. What we do is we perform single qubit operations to diagonalize the Hamiltonian. We simulate the Hamiltonian in its eigenbasis, and then we return to the computational basis by undoing that transformation in the first step. And that's it. So this isn't quite fully general, unfortunately, because of the fact that you can have a Hamiltonian that's a sum of non-commuting terms. So if it's a sum of XX and ZZ, because these two operators aren't diagonal on the same basis, we can't apply directly the same trick. So instead, what we do is we do a time-honored approach. We use a Trotter formula. Trotter formula says, okay, well, if we ignore the fact that these two operators don't commute, then we can write the exponential of the sum as a product of exponentials. And the error net ends up scaling quadratically with the evolution time. So it's only very accurate for extremely small steps. But fortunately, we can always break a long simulation up into a sequence of short steps. And if we do that, then we end up with scaling. If we break it into R steps, then we end up with scaling. It goes like t squared over R. So we can always make R as big as we want in order to make this error arbitrarily small. The big catch is, well, unfortunately, R has to be pretty darn big in order to get this to work out. So you'd like to get a better trade-off in some cases. So in that case, the answer is to use higher order product formulas that actually respect commutators and simulate their action. So an example of a slightly higher order formula is this Strang splitting here, which is just like the ordinary Trotter formula, but it's symmetrized. And the reason why I discuss this is because this formula is actually the basis behind a much more powerful approximation building technique, which is known as the Suzuki formulas. And the idea behind it is, well, we start out with this initial approximation S1, and then we build a higher order approximation by doing this following step. For some value of S1 that you can compute, what you do is you take 2 time steps forward using this integrator S1 between 0 and t. You get almost to the end, and then you do something bizarre. You take a step back, and then you do another 2 time steps forward. Although this looks counterintuitive and it's something like you wouldn't want to do, you'd imagine you'd always want to go straight towards the end. It turns out that by doing these evolutions in this kind of convoluted order, what you can do is you can cancel out many of those error terms. So rather than having an approximation which is order t cubed, this will end up giving you an approximation that's order t to the 5th.
Can you back up to the previous slide?
Sure. Previous one, like this one?
Okay.
Okay.
I'm not asking you anything, just wanted to soak it in.
Sure, no problem. Sorry, there is a lot of material here. My apologies. Okay, so this is a method that you can use to turn S1 into a higher order integrator. And this method doesn't just end there. It turns out you can plug S2 into the same sort of approximation building thing and make S3, which will be a 7th order formula. And in general, you can do that. And here are the coefficients that will end up working it for generating a Kitaev order formula from it. So that is the method that, in general, is used in order to fully optimize these simulations. So by doing this, we end up getting near linear scaling of the circuit size with t. And without using this optimization, by staying with a low order formula, then we'll end up getting something that'll be like t to the 3/2 or something worse like that. So that is the technique that in general will allow you to get around these problems involving sums of Hamiltonians. However, a question you might ask is, what the heck does R have to be? Can you give me a value of R and promise that if you choose this value of R, then the error will at most be epsilon? And in general, upper bounds have been proven. The 2 best results out right now are these results. And they end up predicting that the error in the Kitaev order Suzuki integrator minus the actual evolution is upper bounded by this over here. Numerical evidence suggests that this upper bound is far too loose. It can be too pessimistic by 3 to 4 orders of magnitude in some cases. But nonetheless, the results prove that if you take a value of a number of time steps that's greater than or equal to this quantity, which is derived from the error estimate here, then you guarantee that your error is going to be less than epsilon. So that's the importance of this. It promises that your error is less than epsilon. And this is especially important for simulation because it's hard to assess the error in a simulation you can't compare to the output of a supercomputer. So it's important to have bounds on the error. But if you don't need to be rigorous, then you can take R to be whatever you feel like. So, and furthermore, one of the things that's important is optimizing your choice of R is also important because the total cost of implementing a simulation algorithm is proportional to R.
I lost track of what K is.
Okay, K here should actually be chi, which is the order of the Trotter-Suzuki formula. So I'm sorry, that's a typo. So again, just to summarize what the strategy is we want to simulate an exponential that's the sum of 2 non-commuting terms, and we use one of these high-order splitting formulas to break this up into a sequence of exponentials that are just like the kind that we discussed previously. And then we use our circuit decomposition intuition that we developed from that in order to handle each of those independently. And that's how you go about building a simulator. The question is, how do you automate this in a fashion that actually isn't more work than doing a simulation in the first place? So the last thing you want to do is make a Rube Goldberg contraption type automation procedure. Fortunately, our algorithm is a lot better than these examples of automation. So the idea behind our classical algorithm is this. What we do is we begin with input, taking an efficient representation of the system Hamiltonian as a string. We require a parameter that tells how local the Hamiltonian is, i.e. k. Say it's a k local Hamiltonian. The number of qubits that the Hamiltonian acts on has to be provided as an input. And also, the desired evolution time and the desired number of time steps used in the overall evolution have to be provided as input. Then the circuit design algorithm automates the reasoning that I discussed previously and outputs a string that represents the quantum circuit. So now let's discuss what the inputs and how to encode the inputs and the outputs using this. And there's many ways. This isn't unique. It's just something that was that we arbitrarily came up with. So the idea basically is this. A Hamiltonian in general will look something like this. It'll be the sum of these local terms with different weights in front of them. So the way we encode it is we store the weights as a vector. So we store each of those as this vector I denote boldface A, and then we also store strings that encode each of these individual terms. It'll tell you whether it's an x times an x or a y times a z. And if we store two strings that encode those pieces of information, then we have a complete description of the Hamiltonian. So that's the basic idea. The way we practically do it is as follows. We encode each of those terms as a concatenation of two strings. And the string represents, the first string, L, represents the numbers of the three types of Pauli operators present in a given term. So, for example, in this x0, x1 case, there's two x operators, there's no y operators, and there's no z operators. So we store that as a string 200. The S, on the other hand, will tell you the locations of those Pauli operators. So in this particular case, it stores the locations of the x operators, the y operators, and the z operators separately to avoid ambiguity. So in this particular case, there's no y or z operators, and the x operators act on the 0th qubit and the 1st qubit, respectively. So that's how we would go about encoding that. And a full example of the Hamiltonian is given here. So this represents the encoding of the total Hamiltonian. This description is also efficient for constant k because of the fact that we only need a constant size string to represent each term. And furthermore, there's n to the k such terms, and k is a constant. So for k local Hamiltonians, there's a polynomial number of terms, where n is the number of qubits in the system. And each of them has constant size, so therefore the output is polynomial, the input is polynomial, and therefore it's reasonable to work with.
How is the string in 0 is different from regular 0?
Oh, that just refers to the empty string.
0 one list here?
It means null.
I think null list.
This is null list, and standalone 0 is one element list, right?
Yes.
Okay.
Yes. So, in this particular case, the output is similarly encoded. So we encode a C0 gate in the output is just the string C0 and I and J followed it. We refer to a Hadamard gate is Hadamard times identity, and a pi by 8 gate, or sorry, not identity, a Hadamard and then I, indicating which qubit it acts on, and a pi by 8 gate is just S and the qubit it acts on. So that's the output, and the output is designed to be implemented in order from left to right. Okay? So the way that this will end up working is this will end up producing, you begin with a description of a Hamiltonian that you have at an abstract level. You encode that as a sequence of strings. You feed that to your compiler, and your compiler will output another string, which can then be directly interpreted as a quantum circuit. So that's the overall idea. And again, the strategy that we use to go about and achieve this is we use a Trotter-Suzuki formula to turn our simulation into a product of exponentials. We then generate a simulation circuit for each exponential and concatenate them together to come up with a simulation circuit that describes one of the R time steps. The final step is very easy. We just glue our identical time steps together, one after another, and that will enact the overall simulation. So now I'd like to discuss how to encode the output of the Trotter-Suzuki formula in just a little more detail to make it in a fashion that fits inside that paradigm. So the idea is that using some algorithm, doesn't matter exactly how, we end up getting this sum of individual Hamiltonian terms, that I've denoted, unfortunately, H1 through H3. These are not Hadamards. I mean, these are actual products of Pauli operators. So we have some output that looks like this, and then what we do is we encode each of these terms as a string. Again, we don't want to store them as a matrix because the matrix is very big. So we can uniquely specify each of these terms over here by specifying the Hamiltonian, which is done by giving the weight of the coefficient, the number of each type of Pauli operators in there, and their locations. So that specifies the H1, and this specifies the evolution time for the first term. So we can come up with a string representation for each of these exponentials that are in the product.
Why are magnitudes the same?
Excellent question. In general, they won't be the same. The reason why is because of, let me go back a bit, this.
Oh,
Notice that these are not just the same length either. This backward step is much longer than the previous two. So in general, many of these durations will be the same, but some of them will be different. So I need to specify which ones are
for the
different.
base trotter, they were all the same
For the base trotter, they're all the same.
before you did this.
Yes.
Okay.
Okay, so then we use this output of the algorithm as a sequence of strings of this form as input for our circuit construction algorithm. So our circuit construction algorithm is pretty straightforward, although it looks kind of ghastly. So what we do is we take as input a description of one of these exponentials. And then what we want to do is we want to output a circuit that simulates it. And the way we do it is we take each element in SIX, which is the description of the locations of each poly X operator in a term. And then we want to transform to its eigenbasis. And we do that by applying the Hadamard transform on the qubit in which it acts. So that's what this first step says. Second step says, well, do the exact same thing for the Y operators. Instead of, but we have to use a slightly different diagonalizing operator. We've got to use this ghastly thing here. Okay, but it's intuitively exactly the same. So after these two steps, the term, the individual exponential has been transformed to its eigenbasis. So then what we do is we find some particular value, L, which is the maximum entry of all of these things here. And the reason why we do that is because I mentioned that we want to compute the parity when we do these things. And we'd like to not use an extra ancilla bit to store that parity. So what this step does is it finds arbitrarily the qubit that this term acts on that has the highest label. And it does the appropriate rotation just on that qubit. So that's what this does. It finds the qubit with the highest label that's non-trivially interacted with. Then, for each element in this SI over here, i.e. each location that at least one poly operator acts on, we need to compute the parity. And we do that by doing a C0 with the control being the gate that has the thing in it, and target being the last one. And obviously we don't do a C0 from itself onto itself. We can skip that. So we continue through. The next thing is the RZ operators that I alluded to, they are not in our fundamental gate set. So we have to transform them into things that are. And to do that, we use a Solovay-Kitaev algorithm as proposed by Nielsen and Dawson. But there may be more efficient versions that could be in existence soon. But I should, of course, mention that in general, there are, in particular architectures, RZ gates are things that are relatively natural to carry out, but we stay away from that because of the fact that arbitrary precision rotations aren't something that's a very physical resource. So we prefer to consider what happens by discretizing it into our fixed gate set. These last three steps are pretty self-explanatory. They just undo all the stuff that's done up here. So that's it.
So on step 5,
Yes.
we had some epsilon as an input to the overall algorithm, right?
Right.
So how it translates into a tolerance requirement?
Excellent question.
For Solovay-Kitaev.
So how that translates is we have you from your value of r that you use for the number of time steps and the order of the Trotter-Suzuki formula that you use, you know how many exponentials you're going to have in your sum. So you want the error in a Solovay-Kitaev algorithm to be like epsilon over the number of exponentials, because of the fact that the error grows at most linearly with the number of such terms. So you can guarantee then that the error will be at most a constant multiple of your error tolerance if you do that. Okay? So that's what you do. Now let's put this all together and again describe how we would go about and build the overall simulation from this. And it's, again, more or less what I said. We apply the Trotter-Suzuki algorithm with the inputs that describe the particular Hamiltonian and compute a sequence that ends up describing the set of exponentials that are needed to perform one small time step. Then we glue our such time steps together and output. That's basically it. So now that I've described the overall algorithm, I'd like to talk about some applications to show how well this ends up performing. So the classic, one of the classic examples that's worth talking about is the Honeycomb Model, which is important because of its relevance to topological quantum computing. So this is an example of a physically two-local Hamiltonian. The reason why is because each qubit, represented by a circle here, is coupled only to nearest neighbors. And furthermore, each of them, regardless of how big you end up making a system, each of them is only coupled to at most 3 other qubits. It's because of the fact that the number of couplings doesn't increase with the size of the system. It's physically local, not just k-local. So that's what we... Difference between white and black. There's a... okay. Basically, they're not of the same class. All the x's can be translationally mapped onto each other, whereas the couplings have a different sort of form from the whites and the blacks. So that's why they're listed differently.
You have different recursion code depending on which side you're reading.
Yeah, I don't see it. So if you take a look for the Z gates, or sorry, the white over here, it's coupled down by Z here. We can't just translate that down to this lower one without rotating and make these two equivalent. All the rest of these, though, can be just mapped directly onto each other. So it's a rotation. So when we go about doing a simulation, there's 3 different types of interactions that we end up getting out of this. And each of those interactions can be decomposed into a simulation circuit that will handle them. Going through the work that I described previously, these describe the YY couplings, these describe the XX couplings, and these describe the ZZ couplings. So we just have to glue all of these steps together, and then we can figure out the cost. Doing this, we end up finding for a fixed number of time steps R, the following number of gates required for the simulation, which is a neat result because of the fact that nobody actually has, before this, to the best of my knowledge, had provided a decomposition into fundamental gates like this. And again, you can do better. We listed in terms of Z rotations because of the fact that the Solovay-Kitaev could give slightly different results depending on what your rotation angles are for the given time. So we...
What's the N here?
N is the number of qubits in the system.
Oh, lattice.
Yeah. And the value of R ends up scaling like this. And you can treat little m here as being order n in this particular case. So roughly speaking, this ends up scaling like n squared. So it's very efficient. Similarly, we can also take a look at simulating models of superconductivity, particularly pairing models between electrons. And Wu, Bird, and Lidar showed that such Hamiltonians can be written in this particular form over here. So this is a form that also is amenable to our simulation techniques. So we can actually simulate that, actually even using the exact same circuits that we described for the Honeycomb model. So doing the exact same thing, gluing all of them together, we end up finding the following costs. And one of the key things to notice is before we only had n times r basically. But here we have n squared. And that difference is because of the fact that the model, if I go back, you'll notice it actually isn't physically local. There's coupling between every other qubit in the system. And that ends up fundamentally changing the complexity. So our result ends up giving performance that scales like n to the 4th and slightly worse than linear scaling in the time you want to simulate the system for. And this is much better than the previous result, which is nearly quadratically worse in terms of its simulation with time and has a worse factor of n as well. So that's what we end up getting out of this. In general, we can talk about what this thing will look like when we apply it to an arbitrary k-local Hamiltonian. and an arbitrary physically k-local Hamiltonian. And the number of operations that we end up getting ends up scaling something like this. It ends up scaling a little bit worse than n to the 2k for a generic k-local Hamiltonian. Whereas for a physically k-local Hamiltonian, it's a little worse than n squared. That's a big difference for a large value of k. Even for k equals 2, that's a nearly quadratic difference. So that's one of the reasons why denoting the difference between these two different classes of local Hamiltonians is important for our context.
What's the meaning of the set membership symbol here?
Okay, so what I mean is it's like I would use for big O notation, but I can't put a big O around the outside of it because of my use of little o and the exponent over here. It ends up making it a little bad reading. So the way to read this is it asymptotically scales at worst as the following function.
So it's belonging to this asymptotic family.
Yes, exactly.
Okay.
So how do we optimize these circuits further? Now that I've provided a rough prescription for how you can go about doing it. And the way, one of the ways that we can do this is that actually many of the terms in the Hamiltonian will commute. And if we just were to randomly put these commuting operations into the Trotter-Suzuki algorithm, then we'll kill the depth of our circuit. Because there's all sorts of operations that in principle could be done in parallel that no longer will be able to if we just naively put it through. So one of the ways we can optimize our results is by finding the terms that commute with each other and then grouping them so that we can execute them at the same time. So the way that we do that is as follows. So you can see an example of this for this particular Hamiltonian. And here are two different ways that we can use the Trotter formula to approximate the time evolution operator in this case. In the first case, you notice that these two operations in the brackets commute because they act on different qubits. Whereas in this particular case, we can't commute any of the terms. So if we go through the circuit design algorithm, we find that the resulting circuit for case A looks like this, and in case B, it looks like that. And it's a little hard to get an eye for, so I drew this out so you can get an idea of what the circuit depth looks like. And you'll notice that in this particular case, the depth is reduced in contrast to the other one. So that is one of the things that we can do. So how do we end up finding whether or not terms in the Hamiltonian commute? The way that we do it is we take a look at the following relationship. So it turns out that an equivalence for two terms in the Hamiltonian commuting is this condition over here. So basically what I mean here is I mean the size of a particular set of locations where the Pauli operators both have disjoint action is at most is equal to 0 mod 2. So there has to be an even number of locations where they both have different actions. And you'll see things like this in, say, the toric code, where you have XX couplings and ZZ couplings that are happening on the same qubit, but actually the two terms commute because there's an even number of interchanges. And this refers to this. This criteria captures that, as well as the case where you actually have different actions on each qubit. So that's what we get out of it. And basically, our grouping algorithm for grouping these terms is really straightforward. We just compute that term, and then we group them all together in a fashion that has all commuting elements in a particular group done first, and then every element in the next commuting group is done after that, and so on and so forth. So that's how we do that. Well, the question is, what does this end up doing for our algorithm? And there's actually substantial improvements in the complexity for the two cases. So in the case of, so let's go down. So in these particular cases, we end up getting scaling with the number of qubits that goes like n to the 2k plus some small subpolynomial function minus 1 in general using grouping. Whereas if we didn't use grouping, you remember the number of operations required, which is equivalent to the time if we don't use parallelism, ends up scaling at worst like this. So we end up getting a reduction by a factor of n by grouping in the worst case scenario by using this algorithm. For physically local Hamiltonians, it's even better. We end up going from something that's like n squared in our previous work to something that is like n, if we use grouping and we perform all operations that commute in parallel. So as a result, this can actually really, really seriously improve the performance of our algorithms in architectures that permit parallel execution. In architectures that don't permit parallel execution, it's not clear what form of improvements this will end up giving. So to conclude, we present a constructive argument that our constructive algorithm that generates circuits for simulating many-body systems. Our circuits are more efficient than previous constructions that have been considered. And also, as an important point, we don't actually require any n syllabits for this. We use n qubits to simulate n qubits, which is a big advantage for people who don't, well, for existing quantum computing computer implementations that are limited to at most 12 qubits or so at present. And also, we show how to exploit parallelism, which can lead to improvements in the execution time for things that allow parallel execution. There's a few open questions. One of the important questions, I think, is, well, this grouping idea that we came up with, is there more that we can get out of it? By expressing the terms in ways that commute, are we actually reducing the error in a Trotter-Suzuki formula more so than what the upper bounds say? Equivalently, when we do this grouping, every term that commutes has a simultaneous eigenbasis. But yet, when I was describing that previously, I was at every step, even for the commuting terms, transforming to the diagonal basis, performing a simulation, transform to the computational basis, then transform to the diagonal basis. In many cases, an intelligent choice of the diagonal basis may allow us to forego almost all of the basis transformations. So that is one way in which this can be improved. Also, the question is, can we use compilers that actually optimize the circuit output in order to improve the performance of these really naive simulation circuits that end up coming out of this algorithm? I would be very surprised if they couldn't be, in many cases, substantially improved. Also, in general, we might not be interested in every possible property of the quantum state. For example, for these systems, we might only be interested in the average magnetization or some quantity like that. And in those cases, do we really have to keep track of every aspect of the quantum system? Are there some things we can throw out because they won't affect it? Well, that's an open problem, and one that I hope ends up getting addressed, but I don't know the answer to it. And also, a final question is, can these ideas be used in order to design very efficient simulation circuits that can be used in order to bootstrap a quantum computer? Well, thank you very much.
So, concerning your second item from the top,
yes,
I would be very much interested in a case study. If you would have some cases where you have manually shown how to reduce the circuit size.
The second point here.
Right. So
that would be something that would be interesting.
This case study might help me to actually test some of circuit optimization ideas.
Okay.
Concerning the third from the top, it looks like a projection exercise. Can we find a projection to some system with a smaller qubit size, for example?
Right.
To see, and while at the same time making sure that whatever projection loses is not what we are interested in.
That's exactly the idea.
Yeah, and
Couldn't you also start from the Hamiltonian design? Couldn't you put less into the Hamiltonian of the things you don't care about? It's a model anyway.
It's a very good question. But in many cases, aside from direct application of perturbation theory, it's very difficult to say what terms you'll care about and which ones you won't necessarily care about for a particular observable. I mean, if one term is 1,000,000 times smaller than all the other ones, then it's a trivial task. But in general, I think it's a hard problem.
And how do you foresee this helping? Might hit the fourth point with all the others.
Yeah.
How do you foresee this helping to bootstrap?
Well, the way I see this potentially having an application for bootstrapping is ideally what you want to do with bootstrapping is you want to have a partially characterized and partially controllable quantum computer that doesn't have access to all of its qubits because of poor characterization. So the idea is you would perform a simulation of how some ideal circuit should perform on a subset of that larger space. And then, based on the outcomes of that, you benchmark and compare the performance of that particular uncontrolled system with different sets of control parameters in an attempt to learn how to control that and increase your number of effective qubits in the system. So you do this, you build a larger quantum computer after reclaiming, say, one additional qubit that you have, and then you repeat this process until you can control every physical qubit in the system.
There's a bigger question, though. You seem to be using implicitly the ideal qubits thing. So, and
you didn't do qubit defects, right?
All your qubits are ideal, and all your gates are ideal.
You're absolutely 100% correct. This analysis is not taking a look at any form of gate errors, any form of gate imperfections other than what happens by implementing the RZ gates via Solovay-Kitaev. So all of this is done in a very idealized model. And decoherence, yeah. So yes, you're absolutely right. There's much more realism that we could build into this. But in many cases, this is going to be device specific. So, and our goal here was to come up with a general circuit building model that's appropriate on any platform. Refinements to these ideas, I think, would be very appropriate for optimizing the performance of simulation circuits in the presence of these problems, which will be specific to an implementation.
Solve the ideal case first. If that doesn't work, you're dead.
You're dead in water.
First make ideal one.
I know there was zero negativity in my comment.
No, obviously. No, the point is, there's a lot of work then to get. I think that might have had to go with the bootstrapping question, because when you're starting about working about a real system, now we've got a whole different layer that makes it even harder.
Yes.
Which is, figuring out how to understand the qubits you've actually been dealt.
And under what circumstances for a real system, you're not going to be able to perfectly control, and you're not going to be able to perfectly reclaim them. So the question, that's why I think it's still an open question and an interesting one to determine to what extent can quantum simulation algorithms be used to build a bigger quantum computer.
And nowhere here did you talk about preparation of the starting state.
I never.
So are we just going to assume that there's a technique?
Assume you can prepare your favorite state,
Okay.
and or equivalently, assume you've got some machine that at the beginning of the algorithm outputs that to you.
Have you implemented a simulator on top of the output strings of this, or this was just the work to figure out how to get the strings?
This is just the work to figure out how to get the strings.
And have you coded all that? Just wondering.
No, I haven't.
Neat. Is this all in the paper that was in the archive?
Everything's in here except for the grouping bit. That bit is being added in preparation for a submission to a different journal.
Okay. I'm just saying, what journal do I look for now?
Well, we'll be submitting it shortly to a new Journal of Physics, and we'll have a new version on the archive, hopefully very soon.
I'm always looking for the updated version whenever it happens.
Exactly. Yeah.
Okay. Neat. Good stuff. Great. Lot to digest. I've read the paper twice and have to go back third.
Yeah, I think there's some improvements that can be made.
So my understanding. Krista, do you have anything else?
Thanks.
All right. Thanks again.
Well, thank you very much. I'm really grateful that everybody came.